The helium atom is an excellent example of using the variational method to calculate the ground state energy, or an upper bound of the ground state energy. We'll start by defining the helium atom coordinates. Then we'll choose the trial function. We'll set up the integrals, and then we'll actually do the integrals and calculate the final energy. So, the full Hamiltonian of the helium atom includes an electron-electron interaction, which we ignored when we first discussed the helium atom in Chapter 5. So our coordinate system looks like this. We have a proton here in black, an electron in red, and another electron in blue. The distance, or the vector, from the proton to the first electron we'll call R1, and the vector from the second electron to the second electron we'll call R2. We're going to assume that the proton, the nucleus, the two protons, are basically stationary. We also have the electron-electron distance, which we'll write as the absolute value, or the distance is the absolute value of R1 minus R2. The Hamiltonian is the following. We have minus h bar squared over 2m, and then we have the Laplacian for coordinates 1 plus the Laplacian for coordinate 2. This is the kinetic energy term of the two electrons, assuming the protons in the nucleus are stationary. The potential energy is minus e squared over 4 pi epsilon naught. And then we have the attraction of the first electron to the nucleus, which is 2 because there are two protons in the nucleus. So it's 2 over R1. That gives us 2e squared. And then we have the same thing for the second electron attracted to the nucleus, which gives us 2 over R2. Now notice these are positive because of the negative sign out here. We then have to add the electron-electron repulsion, which will come in with a minus sign inside the parentheses, and that makes it positive all the way outside. And that goes like 1 over the absolute value of R1 minus R2. So these are the distances between the two electrons. We want to compute the ground state energy, which is the total energy required to remove both electrons. And we know what this measured value has been. It's minus 78.975 electron volts. The problem in doing this calculation is this electron-electron repulsion, because it's easy enough to do the calculation for the direct Coulomb potential, but it gives you a very poor estimate of the energy. This interaction potential, which we'll call V sub EE, is E squared over 4 pi epsilon naught times 1 over the absolute value of R1 minus R2. And this is not exactly soluble. So, if we ignore this electron-electron interaction term, the exact solution of the helium atom is just a combination of the two hydrogenic wave functions, right? So the ground state of the helium atom is R1, it depends on R1 and R2. If we ignore spin, or we assume that the electrons are in the spin singlet, so it's chi 0, 0, then we can write the spatial function as a symmetric function, because the spin singlet is antisymmetric, and electrons need to be antisymmetric overall. And each of the electrons is in the ground state of the helium-like, or the hydrogen-like system with two protons. So psi 100 of R1 times psi 100 of R2. Now each of those, this function now looks like 8 over pi a cubed, e to the minus 2 R1 over a, times e to the minus 2 R2 over a. Now the solution to this is 8 times the energy of the proton. The reason you have 8 times the energy of the proton is because you have two protons in the nucleus. That gives you a factor of 4 in the energy of the ground state, the 100 ground state. So instead of being 13.6, it's 4 times 13.6. And then you have 2 electrons that go in the same state, so you get 2 times that. So you have 8 times E1, which is minus 109 electron volts. This is clearly far away from the actual energy, which is minus 78 point something. So we can get a better approximation by applying the variational principle. So can we get a better approximation by applying the variational principle with this trial function? Well, one would hope so. The Hamiltonian applied to psi 0, this trial function that we have here, which is just a product state of the two hydrogenic-like states, is going to give me 8E1 for everything but the interaction Hamiltonian. Because this is everything but that interaction Hamiltonian is diagonalized by psi 0. And then we have plus VEE, and all this applied to psi 0. So this is our eigenvalue equation. Well, when we close the bracket with psi 0, we get the expectation value of H. The Hamiltonian is 8E1, that's just the expectation value of the first part, plus the expectation value of V sub EE. And this is what we have to calculate. Where VEE is just E squared over 4 pi epsilon naught divided by the absolute value of R1 minus R2. And this is going to be a rather complicated integral. So if we write it out loud, the expectation of value of V sub EE is equal to E squared over 4 pi epsilon naught times 8 over pi a cubed squared times the integral. It's a 6-dimensional integral, so all over R1 and R2, 3-dimensional integrals each, e to the minus 4 R1 over A times e to the minus 4 R2 over A divided by the absolute value of R1 minus R2. And here I'm keeping all the first electron in red and the second electron in blue just to keep them separate. Well, this is what we have to compute. And so we have to do this integral. It's a little bit tricky, but we'll go over the details here. The first thing we want to do is to simplify it by a careful selection of the two coordinate systems. So this is our generalized coordinate system. We have a proton, 2 protons here, our nucleus. We have an electron here and an electron here. And we can simplify the coordinates by aligning R1 along the z-axis of the second coordinate system. So if we take R1 along z sub 2, then theta 2 simply becomes the angle between R1 and R2. And that simplifies taking this absolute value quite a bit. So when we take that absolute value, R1 minus R2, and these are vectors obviously, we get that this is equal to the square root of R1 squared plus R2 squared minus 2R1 R2 cosine theta sub 2. Because clearly now that angle is defined within the coordinate system of particle 2, of electron 2. When we put that into the integral, we get the following. V sub EE is equal to E squared over 4 pi epsilon naught times 8 over pi a cubed squared times the integral of e to the minus 4R1 over A, e to the minus 4R2 over A, divided by the square root of R1 squared plus R2 squared minus 2R1 R2 cosine of theta 2, integrated over d cubed R1 and d cubed R2. So 6 integrals. We now can start to do the integral over R2. Well, that integral will exclude all the terms that have to do with R1 that aren't mixed with R2. So we can ignore this part here, e to the minus 4R1 over A. We can ignore the d cubed of R1. And we just have an integral that has these 3 terms, e to the minus 4R2 over A, divided by the square root of R1 squared plus R2 squared minus 2R1 R2 cosine theta 2 d cubed R2. When we write that integral out in terms of all its variables, we get e to the minus 4r2 over a times r2 squared sine theta 2 divided by r1 squared, square root of r1 squared plus r2 squared minus 2r1 r2 cosine theta 2 dr2 d theta 2 d phi 2. Right? So we have this as our integration volume. Well, the phi 2 integral is really easy. It just gives us 2 pi because there's no phi 2 dependence here. And the theta 2 integrand is a perfect derivative, as it turns out. That is, if we look at this theta integral alone, we have an integral from 0 to pi of sine theta 2 over 1 over the square root of r1 squared plus r2 squared minus 2r1 r2 cosine of theta 2 integrated by d theta. And this is a perfect integrand of square root of r1 squared plus r2 squared minus 2r1 r2 cosine theta 2 over r1 r2. Because if we take the derivative of this, we get the 1/2 from the square root. We then get from integrating what's inside the square root, we get 2r1 r2 minus sine theta. And this goes in the bottom. So you can see immediately that this integrates out to exactly this function. And this is evaluated from 0 to pi. Now at pi, cosine is minus 1. And at 0, cosine is 1. So this gives us 2 terms. We have a 1 over r1 r2 out in front. Then we have the quantity square root of r1 squared plus r2 squared plus 2r1 r2 minus the square root of r1 squared plus r2 squared minus 2r1 r2. Well, we can rewrite this by realizing that this is just a perfect square of r1 times r2, r1 plus r2 squared. When we take the square root, we get r1 plus r2. This one is the square root of r1 minus r2, the square of r1 minus r2 squared. And when we take the square root of that, we have to make sure we keep things in the right order. So that we'll write down this as the square root gives us the absolute value of r1 minus r2. So the order here will depend on which one is bigger. And so you actually have 2 regimes under which this integral can be evaluated. The first regime is r1 greater than r2. So if r1 is greater than r2, in this case, then you get a minus here. You just replace this as r1 greater than r2, then this is minus r1 plus r2. And so the r1s cancel here, and the r2s add up and cancel out with this r2, and you get 2 over r1. So if r2 is less than r1, you get 2 over r1 for this integral. If r2 is greater than r1, then you have to flip the signs here, and you get r2 minus r2 plus r1. And now the r2s cancel inside the brackets, and you get 2 over r2 when you multiply it all out. So when r2 is bigger than r1, you get 2 over r2. When r2 is less than r1, you get 2 over r1. So that means that we've solved this, but we now make this ultimate integral here for the r part of the I2 integral. We have to split it into 2 parts. So I2 now becomes 4 pi over times 1 over r1 times the integral from 0 to r1 of r2 squared e to the minus 4r2 over a dr2. That was for r2 is less than R1. And then for R2 is greater than R1, you have to integrate from R1 out to infinity. And now you have the other form, which gives you, in the integrand, R2 over times e to the minus 4R2 over a dr2. So these are two slightly different integrals, both easily doable. You can do integration by parts on this, with dv is equal to e to the minus 4R2 over a dr2. And you get that for this first integral, which I'll call red integral, I get minus a over 4 r2 squared e to the minus 4r2 over a evaluated from 0 to r1 plus 2 times a over 4 times the integral from 0 to r1 of r2 e to the minus 4r2 over a dr2. And I'm going to do this integration by parts one more time. So here, this first term in the integration by parts does not go to 0 because you're evaluating it not at infinity, but at r1. So you get minus a over 4 times r1 squared, that is when you replace r2 with r1, e to the minus 4r1 over a. The second term, once you do that integration by parts again, you get minus 2 times a over 4 squared r2 e to the minus 4r2 over a evaluated from 0 to r1, plus finally the integral 2 times a over 4 squared, integral from 0 to r1 of e to the minus 4r2 over a dr2. We now can evaluate this second term again, replacing the r2 with the r1, and at 0 this goes away, and we're left then with the final result of this integral, which gives us two terms as well. This gives us minus 2 a to the fourth, a over 4 to the third, e to the minus 4r1 over a, plus 2 times a over 4 to the third power. We can gather up these terms, and we can see immediately that each of these terms has a different power of r1. We have to put this in and divide by r1, and now we have to do the blue integral. The blue integral is basically this one integration by parts. So you get the first term of udv, or uv, is minus a over 4 r2 e to the minus 4 r2 over a evaluated from r1 to infinity. Again, at infinity this is going to go to 0, but at r1 you replace r2 with r1. And then you have the integral of a over 4 e to the minus 4 r2 over a dr2 evaluated from r1 to infinity. This gives us, the first term gives us a over 4 r1 e to the minus 4 r1 over a, and the second term again gives me a over 4 squared e to the minus 4 r1 over a, and the other term goes to 0. So when I put these two integrals together, I get the following. For the red integral, I have all this stuff in the red, and for the blue integral, I have all these things in blue. I won't bother repeating them, but I'll let you read them carefully for a minute. You'll notice that they all look very similar. This term has no exponential. All the other terms have the same exponential form, e to the minus 4r1 over a. And then they have varying powers of a over 4 and varying powers of r1. These two are exactly identical and have opposite signs. They cancel. So this leaves me with this term added to this term with an r1, and this term with no exponential. So I have three terms left. I2 is then equal to 4 pi times the quantity minus a over 4 squared e to the minus 4r1 over a minus 2 over r1 a to the a over 4 to the third power e to the minus 4r1 over a plus 2 over r1 a over 4 to the third power. Now this is just I2. If I can simplify this a little bit more by pulling out common terms, like a over 4 cubed times 2 over r1, which gives me out in front 2a cubed over 64r1, Then inside I have minus r1 over 2 times 4 over a, e to the minus 4r1 over a, minus e to the minus 4r1 over a, plus 1. And just doing a little bit more rearrangement, I get pi a cubed over 8r1 in front, times the quantity 1 minus the quantity 1 plus 2r1 over a, times e to the minus 4r1 over a. And this is the result for integral 2. We can take that and put it into the expression for v sub EE. So recalling where we had this, we had left out the integrals for r1 over a, and this is our value for the I2 integral. This is left over from the I1 integral. We have r1 squared, and then sine theta 1, dr1, d theta 1, d phi 1. And then we have our constants out front. So the angular integrals are very simple now because there's no angular dependence left over in the integrand. So we get 4 pi. And now I can drop the subscript on the radial coordinate just to simplify things and just call it r. And this integral now can be done from 0 to infinity with a prefactor of 8e squared over pi epsilon naught a cubed. Integral from 0 to infinity of the quantity r times e to the minus 4r over a minus the quantity r plus 2r squared over a, all times e to the minus 8r over a dr. Again, this can be done by integration by parts once here, and then these are two integrals, integration by parts once for this, integration by parts twice for this. When I do all that, it simplifies into boils down into something rather simple, and that gives me 8e squared over pi epsilon naught a cubed times the quantity a over 4 squared in the first term, minus a over 8 squared, minus 4 over a over 8 cubed. Bringing all of these onto a common denominator in common terms, I can see how these are going to work out. When I multiply them out, I get a squared over 16 minus a squared over 64 minus a squared over 128. Bring them all over a common denominator, and I get 8 minus 2 minus 1 over 128 times my prefactors out here, which are 8e squared over pi epsilon naught a cubed times a squared. The a cubed partially cancels, and I get 5 halves times e squared over 8 pi epsilon naught a. So this is now the value for v sub EE, the expectation value for v sub EE. There are no free parameters here because a is the Bohr radius. When we replace this is exactly the energy of the ground state of the hydrogen atom with a minus sign. This becomes minus 5 halves E1, which is plus 34 volts. E1 is negative. So the variational principle with no adjusted parameters gives an upper bound for the ground state of 109 minus 109 eV, and then added to that 34 eV, so you get minus 75 eV. Now, if you remember, the actual value was minus 78.9 or so. So while we've made significant progress, we're not quite there yet. We're still about 4 eV or 5 eV away from a good ground state energy. But this is bigger than that energy because it's less negative. And so the variational principle works. It gives you an upper bound, which is not as close as you'd like, but that depends on the selection of an appropriate eigenfunction to start with.